It's great. So let's get started, everyone. So I see everyone talking with each other. That's great. So that's so again, remember that's part of the reason you're here to meet and kind of build relationships with other people in the class. So that's great. Today I suddenly reorganized the lecture plan. Today we're going to talk about statistical phenomena. So to look at the schedule a bit, I swapped what I thought about maybe doing today on anomaly detection. I felt that was better to do on Monday next week instead. That will be a new lecture. It's prepared and everything, but I think this lecture will be better to do first for a couple of reasons. One will introduce some kind of notation and terminology and ideas that'll be useful in the next one. And the other reason is because the lecture today will kind of be a direct preparation for the first homework assignment. The schedule at the beginning, so we can get the homework assignments out and you kind of working and practicing on stuff, is a bit compressed at the start of the semester. The first homework on statistical phenomena is going to be due in a week. Okay, so usually you'll get a little bit longer, but we're getting stuff up and ramped up. It is available now on so on Gradescope. If you can find Gradescope, log into Canvas, click on the assignment, and you'll be able to take a link to Gradescope. You can also click on here. Okay, if you go there, it will take you to the PDF of the assignment that we have posted. We'll always post them on the webpage and on Gradescope, linked off of so Canvas, so you can find it. So you will turn in a PDF through Gradescope. That will be how you turn it in. Okay, it's due at 1 p.m. next week, Wednesday. 1 p.m. So you finish, and then you come to class and learn the next material. You're not working on it during class. If you really hate this schedule of doing it at 1 p.m. consistently, there's nothing really that special about the time. We could move it to a different time. The past people said they would rather have it do it midnight the day before because they liked homeworks do it so midnight. We can do that if you want. But this is so it's going to be the plan. So they'll give you the morning to work on it. Their office hours scheduled Wednesday morning with one of the TAs. So a couple of mechanics about the homework. We provided a couple of templates for homework. If you haven't done kind of stuff in LaTeX before, right here. I don't know if I can point that well. Okay, but this link goes to overlink a generic kind of example of a number of things where you can use that as a template. But we also created the TAs create a specific template where it says here, right? So here, click there, it will take you to a page in Overleaf that's read-only, but hopefully it's read-only. You should be able to kind of copy that over, and it has all the questions written in there in LaTeX and some kind of example commands and stuff. So that will be kind of easy to get you started so inside of LaTeX. Okay. Then we have there are questions. You're basically going to run some simulations, look at them, and then kind of think through the analysis we'll do in class today. Before I talk about that, let me say the point of this homework. The point of the homework is not necessarily because what you're looking at today is kind of one of the most heavily studied things within the field of data mining. but is to get you used to thinking about randomization in algorithms and analysis. Okay, you're going to be asked to kind of simulate some random phenomena, pretty simple ones that we'll go through in class today, about as kind of simple enough that isn't too complicated to actually think about mechanically what's going on, but complicated enough so you see some interesting properties going. Okay, and so it's a random phenomena. So every time you're going to run code, every time you run it, it's going to give you a different result. And you want to say, was the result I generated expected or not expected? How unexpected was it? How kind of complicated was it? And so there's kind of a process to working through this. You don't necessarily just run it once. You run it multiple times if you can. You look at the results in aggregate, and then you have to maybe plot the results in some way. And then you want to compare what you observed with some mathematical analysis. Right? And you have to think about, how does this mathematical analysis correspond with the distributional output I got from running many of the random simulations, and think, okay, did this make sense or not? Okay, so for you living in the world of letting like AI try and do everything for you, well, if you're asking it to do a random process for you, you can maybe you trust the code it wrote and you're doing the right thing, but you might want to check, right? You kind of you want to verify it's doing the right thing, not just blindly run it. Now, when it's either a random process, which we can control, or random data, which we'll think about throughout the semester, it's hard to understand, okay, was this correct or not? How do I verify that this ran like I expected it to run? Okay, and so this assignment is about going through the mechanics of doing that, the basic things. And we're going to look at two simple things, the birthday paradox and the coupon collectors. We'll talk through these today so in the lecture, and you'll have what you need to do the homework assignment, basically. Some examples of, if you want to write stuff in code, or you want to plot a kind of plot something as like a CDF, which we'll ask you to do, we'll give you a little bit of example there. I don't want you to struggle over that. I want you to be working on the core mechanics of how to work with these randomized outputs. Okay, and then there's kind of comparing it to the analysis, and then there's like a small bonus question at the end. Again, the bonus is worth 2 out of 100 points. You can go over 100 if you want to. Okay. All right. So has anyone looked at the homework yet and found it? No. Okay. So a couple people found it. If you have any questions on it, you can post on Canvas generally about, here's a big question I have about the homework. I don't understand something, but don't post potential solutions. Say, hey, here's what I did. Like, is this right? You can't do that. But you can post other things on there on the discussion boards. We will reply as quickly as we can. Usually I'm pretty good about this. And then the reminder, the TAs have office hours next week, Monday, Tuesday, and Wednesday. And I have some Thursday morning and after class. Okay, so you have some office hours between now and Wednesday. Hopefully it's not too it does not take too much time. I realize the schedule is compressed a bit here. There are surprises. I'll try and be flexible as we get going on this. Yes, okay. Also, the video from Monday's lecture seems to have worked correctly. Hopefully it's working correctly again. There's a link now where this V is that you can click and find the video. Again, I encourage you to come to class. I think it's better for a variety of reasons, but if you miss something or you're falling behind, there's videos online. So, okay. Let's see, one more thing. I changed one thing in the syllabus I just want to bring up. I changed the percentage of the homeworks and the test they used to be 35% from homework and 25% from tests. I kind of made them both 30. Now, with you drop a homework, each one is worth 5% of the grade. So that was kind of aligned with what I said yesterday, but factoring in the dropping part of it. There are a couple of other minor updates to these things, but if there's anything major, I want to make sure I announce it and things are transparent. So that's what I'm doing. Okay, any questions on how things work from last time before we get in the lecture? So great. Okay. Yeah, okay. So most of the lectures will be me lecturing on the iPad and projecting on the screen here. Yeah, and I'll keep trying to work on making sure it's clear, but as I needed to rust out the first few lectures here. Okay, we'll be talking about kind of two, maybe three phenomena here, and we'll be thinking about so we'll be looking at data. This is data mining class as part of the data science curriculum. Okay, and we'll be thinking of having a data set X, and this will be, and usually generically, I'll say a data cell represented as an uppercase X, and we'll often think about this as a set of these elements, X1 through Xn. Okay, so they're going to be a set of n things. If I just quick review, if I use the curly bracket notation, like here, that means it's a set. That means the order does not matter. Okay. Okay, and we'll typically be thinking about X is drawn from some distribution. Okay, so this will be a distribution, and it's going to have a parameter or a set of parameters theta. Okay, and I may change this notation a little bit during the semester, and I'm not going to really talk. It's not going to go into measure theory about what a distribution is, but think there's some sort of phenomena we're going to draw data from this kind of from the distribution, and we should think about this as observations of the world. Okay, so we're interested in studying some part of the world. Okay, interested in studying some part of the world. We're observing some part of the world. We're studying kind of the galaxy, some growth of a plant, some like the data on like a router in the internet, and we're making observations of the world. Okay, and so this observations, we're saying that there's some distribution of things we could see. I'm drawing a random student from the class to gather some information about. I'm making these kind of these observations. Okay, and we're going to have that each xi is one observation. Okay, so each of these data points is going to be like a data point is one observation. I haven't told you what format it is now. For now, it's very generic. This lecture and the next one will keep to a very simple version of the format, and then we'll think about more complicated things as we kind of go through the semester. Okay, and let's look more carefully at this notation here. This notation, when I write that, if I write x kind of a squiggle from d, so theta, this means that x is kind of drawn from. Okay, so that means it's making observation according to the underlying distribution. And again, we're not going to go through the measure theory of what this means, but there's some sort of space governing the things I can see, and I'm making a random observation from it. And I'd like to highlight that I'm going to assume these are IID. Okay, these are IID observations. So IID means, this means independently, spelling on the fly is tough. Okay, independently and identically distributed. When I first saw this for the first year, I saw this acronym, so IID, R2 in grad school. I did not know what it meant. Okay, people, statisticians wrote IID, or someone wrote that, and you type it into Google, and Google didn't give me an answer. And I kind of struggled not knowing what it was meant. So I want to make this very clear. It's really important. Independently and identically distributed. That means every one of the observations, x1, x2, x3, and so on, is drawn independently from the distribution D. That means drawing of one does not affect the draw of any of the others. And identically means they're all drawn, I assume, from the same distribution. So the fact that I saw the first thing there's not like a time ordering, like they must always get larger, or the distribution doesn't change over time. We may deal with cases where we want to model that, but typically we might say, okay, during this time period, everything was the same distribution, and then maybe it changed at a different time period. Okay, so this IID assumption usually underlies things, and this is kind of the basis for most of the way we think about analyzing statistics and machine learning. Okay, and in data mining as well. Okay, so we're going to really be making this IID kind of assumption about the data very strong. Everything is independently drawn. All the observations are independent, and they're identically drawn from the same distribution. Then our goal is to understand this distribution, what's going on. And maybe we'll make a guess of this distribution. We'll see, did we align with this guess, or did something anomalous occur? And that'll be the lecture next week. Monday will kind of be about that question. Okay, how to formulate and think about that. Okay, so all right, so this is the basic premise. Yes, question.
Is it a universal set? Like, if suppose we consider another set Y, and like if we take some elements, those elements should also occur in D. Is it like that or no?
Yeah, I have not said anything about D, about what the kind of the space that D is a probability distribution over some space. I haven't told you what that space is. I've potentially not specified it to keep it general. We're going to go through one concrete example today, a different one the next Monday lecture that'll be simple and concrete, and we can really analyze carefully. And then we're going to see a whole bunch of things that can fit in this paradigm, as long as you don't try and specify too much. Okay, so we're going to think about a wide variety of things, but in this paradigm. And so there's some space of types of observations we can see. Well, if we're computer scientists, they have to be encoded in bits at some level. Okay, but if you're a mathematician, you might not care about that, right? It could be some continuous real world thing, right? Okay, so we'll keep this vague, but these are good questions. We'll come back and think about, what is this distribution? How do we think about it? How restricted is it? And then that will affect how we do this. But it's kind of I'm going to mix between very general things these first two lectures and fairly specific examples that we'll go through, and then we'll try and build things up through a longer example over a few lectures. All right, so let me get into the specific example now. We're going to assume that the domain of our distribution theta and kind of data x is what I'm going to call, so it's going to be a square bracket around M. This is going to be a set 1 to up to, so M minus 1 is just a shorthand, okay? It's a set of M things, and I'm going to use the integers starting at 0 up to M minus 1 to represent those things, okay? But in kind of this can model, it models things like all the all the IP addresses, right? There are like is it 16 or 12 to the power 10 different IP addresses? It's a huge number. M is huge for IP addresses, and they're all a number, and there's some relationships between them, but we're just kind of keeping track of these different items. It could be all the kind of the common words in the English language or in across multiple different languages. They're about kind of, here was M is, was it like 16 to the power 10 here? For M here is maybe, so roughly like 100,000, right? So there are roughly 100,000 commonly used words in the English language. If you look at all the tokens indexed by these large kind of models, they look at the subwords instead of words, and it's about the same number. If you look at all the words ever written, it's around 300,000 probably, and that can include things like emoji and some fairly common misspellings, but so it's around 100,000. This is a big, like a big number. It could be all kind of people in USA. This would be, then you would have M equal about, was it 3.8 million? Okay, so I can have a representation for all the people. Okay, and so I want to then kind of draw a distribution where every time I observe something, it's going to be one of these elements. Okay, we're going to abstract this into just a set of size n. Okay, but it can model all sorts of these different things. Okay, and now if we think about IP addresses or words or all people in the US for responding to a survey, it's not going to be uniform. There's some underlying distribution. Some are more likely than others. In this example, we're going to assume, we're going to now assume that for xi drawn from d theta, the probability of xi equals to j equals 1 over m if j is in M, right? If j is twice m, so it's not in the set, then the probability is 0, but so equals 0. So otherwise, but everything is equally likely. Okay, so we're just going to model this case. Okay, so all IP addresses equally likely, all words are equally likely. I'm drawing one at random. I'm drawing a random person. I'm trying to do a survey for polling purposes for elections. I want to get a random selection of a person. Okay, this is what we're going to model. Okay, and in particular, if you use a hash function, okay, we're going to be able to generate the idea of a hash function. You should be able to generate random values between 1 and m for some domain. Okay, so there's this duality, this kind of, or not duality, but kind of different ways of thinking. I want this to model data, and we'll think about that. But we're going to switch now to thinking about this from an algorithm's perspective. In an algorithm, we can actually generate randomness, and then we can analyze the algorithm itself. All right, so now we're going to think about a let me call this a random, so hash function. Okay, and I'm going to have I would like to get a hash function that is going to, it's not going to take anything as input, but it's going to output something in this domain. Okay, and I want that or it's going to take. Sorry, let me. It's differently. It's going to take something as input. Technically, you often want to hash. So so some string. So you push in some string of symbols. It might be a number. Actually, kind of Python allows you to kind of use MD5 to kind of put a whole bunch of objects in, and it will output something as that's what they call a hash. But this is a random hash function. So there's some sort of string from some world as the input, and it's going to output something, and it's going to have the property that the probability of H of two items, I, equals the probability of J of two different inputs is going to be equal to 1 over M, where if I is not equal to J. Okay, so this basically they make this work by for a kind of effectively a random for two inputs that I don't know what they are ahead of time. Or for one input, it's going to basically map to some random location in this space of size M. Okay, and we're going to think about this M as is going to be an array. Okay, that we can index into, right? 0, 1, 2, 3, up to n minus 1. Okay, we're going to index into a random array, and so a hash table works. This part of how a hash table works is going to take some object and it's going to hash you to a random spot in the array. And if you hash that same object again to check if it's in your hash table data structure, you want to check if it's there. So you want the object ID to hash to the same spot every time. Okay, so what this means is that H is going to be deterministic. So it's not. So if I hash the same thing twice, it should go this. It has to go to the same location. But I have this statement here about the probability. So how does this make sense? Okay, so we're going to draw H from a distribution of hash functions. And the probability is with respect to this distribution of the hash functions. We're going to choose one hash function, then it's going to be deterministic. So a common way of doing this is to assign H a value A, where A is going to be salt, and this is going to be chosen at random. It can be like a random string. Okay, so it doesn't really need to be random. It just needs to be arbitrary and chosen in a way that does not depend on the data if you build your hash table correctly. So the randomness is still kind of not really totally needed here. You can generate this randomness using a utility, generate a random number using utility inside a programming language, or measure the variation in the CPU processor speed to try and pull something that you can't observe to get something random. Okay, but you're going to get this hash function, and this will often be, and one way of implementing this is to take some complicated function. This is, and I'll go through some examples, where I'm going to take in my string I hope to kind of hash here, and that'll be from this alphabet. But I'm going to also concatenate this with the salt. Okay, so I'm going to take this salt here, and I'm going to concatenate it into the function. So the function sees them both together, and because the function is defined and the data doesn't know A, it effectively works, it's arbitrary. You can't distinguish between these. So this is in practice how it works and how you get something that will roughly work with this probabilistic problem. Okay, so we're going to be drawing a hash. We're going to pick a deterministic function that's going to work as our hash function and choose a random salt, that random salt will cause the output to be kind of indistinguishable from and it's going to cause it to different things that are basically going to be mapped to different points in the hash table. Okay, and because the salt does not know what the data is, it's not going to depend on the data, and it's going to scramble things up for us. Okay, so this is the mechanism, and I'll give some examples of hash tables next. Yeah.
So we're picking one salt instead of.
Yes, so when you pick the salt, it becomes deterministic, but the choice of the salt is where all the randomness comes from, right? So the choice of the salt is random, and that will allow you to have these random sort of guarantees that you can then experiment with. Yeah. You have to store the salt, correct? Yeah, so your deterministic hash function that you store is this H, which is really H sub A, right? And it's going to use this other function F, right? So F is going to be a fixed deterministic function that is predefined, but the A is what gives it the randomness. So you store F, which is built in. I'll give some examples. And A will be your key that allows you to kind of make it deterministic. But that choice of A is random, and that's where all the randomness will come. Okay. So hopefully idea of hash tables, probably you saw this in maybe 24 data structure class, 2420, or discrete math class, maybe. Yeah? You've seen hash tables before? Okay, so this is not too unfamiliar. Okay. All right. Okay, have you not seen a hash table before? This is kind of a new idea. Okay. Well, hopefully we'll still, if you haven't seen it before, we'll still see what you need to follow us along. Okay, so what we need is going to be a complex deterministic function, which will be F, which is going to take in our string, right, or whatever our input is, whatever the data thing is the input, and the salt, these concatenated together, and it's going to map to some large, structure of size M. Okay, so some M values. And so let me go through some common things. There are fancier things out there that if you really want to use this for building your own hash table, you want to kind of, you can get more speed and a bit better randomness by digging into these things, but I'm going to kind of conceptually tell you what the kind of the main ideas are here. Okay, so one example would be a kind of so the SHA-1 function, and this is, I believe this came from cryptography, where the idea is that it's hard to invert F, right? So F to the -1, if I know the output, I don't want to be able to figure out what the input is, right? So it's hard to understand the inverse of this. Okay, and this is useful when you have cryptography and you want to have random keys and hide them. And SHA-1 was kind of an early version of attempts at this. It's probably not the best thing, but it's built into most programming languages. It's a very common historical thing. It's everywhere, and it's a good example of this. Maybe you don't use it for crypto, but for this, it should work totally fine. Okay, and a lot of languages allow it to take in kind of an arbitrary string. Yeah.
So, just a little bit confused here. The salt that we're using in this function, this random value, is salt the technical term for it, or could this string salt be any string?
It could be. So salt is technical term. Yeah. I don't know, like, yeah, I guess if I say it's technical, it's a technical, it's kind of an informal term, but it's become a technical term. Yeah, so it could be any string. This is like this I used a variable a here, right, in this slide, but it's some string that's giving me the randomness. Okay, it's independent. The data, the string part is my data I'm putting in, or some things I'm comparing, and the salt is the random part of it. Okay, but whatever, I've concatenated these together, and I just want a function that's hard to invert. And the SHA-1 is an early attempt at this that's widely used. There are other ones you could use, but it's hard to invert. And if I do this, it maps, well, let me just say, this maps to m with m something like 2 to the 160. I think gives you 160 bits as the output. And you can maybe take a subset of these bits and it should be fine if you want to have a different value. A seed? Yeah, so a seed is technically something different. Most efficient random number generators, they actually pre-generate a sequence of random numbers. Okay, and there's a fixed ordering, and the seed basically tells you where to start that sequence. So a seed is similar to this, right? But they work basically the same way. So if you want to think of how you would use a seed, then this is it, right? But the salt is something a little bit more general than a seed. Yeah.
How does SHA-1 guarantee you?
Yeah, so it's not designed to do that, right? It's designed to be hard to invert. Okay, that means if I have two things, knowing that two things are at the same location or things next to each other or some value should not tell me anything about what the content is. And in principle, that means that the probability the structure of the data, the input string, does not tell me anything about the probability they collide. Okay, so I'm not directly trying to guarantee this, but I'm getting this as kind of indirect consequence of the uninvertibility of the function. That I can't tell anything from the value of the output to tell me about what the input is. And that tells me that two things that are related in the input shouldn't hash to the same location. Fine. Yeah, that's it's a really good question. And I haven't directly given you an answer to that, and I won't for any of these other examples as well. But this is the principle, and variations of the things I'm going to describe are generally what people use in practice for this. So that's what I'm aiming this part of the lecture for. Okay. Another common thing that works if you want to implement something yourself, multiplicative so hashing. And so this is a fairly something like SHA-1 is meant to be a black box, more or less. I think people have opened up SHA-1, but there's the SHA-256, and there are a whole bunch of other versions of this. A multiplicative hashing is, I should think of this as numbers. Now this sigma t must be kind of this should be kind of some real value, or it should be some should be a real value, some sort of number here. Let me write this clearly. So I need to first convert it into a large number, like a large integer, and then I would define multiplicative hashing of x as my input. Okay, I'll use x here. Okay, this is going to be I'm going to do x multiplied by a. Okay, then I'm going to take the fractional part of this. Okay, so what frac of 17.23 is going to be 0.23. So I'm only going to take the fractional part of it, the part after the decimal. So now a is going to need to be I'd want it to be a number less than 1, some large string of bits after the 0, okay? And then I'm going to multiply by m, and I'm going to take the floor of this. Okay, so I'm going to take, and that's going to give me the integer part, right? So if I do 17.23 using the floor operation, this is going to give me 17, right? So this will index into one element of the array, right? So this part is indexing into the array, and this fractional part multiplying by a is basically I'm multiplying by some large, complicated kind of number with lots of things after the decimal point, okay, that I won't be able to understand. And then I'm going to take just the fractional part of this. Okay, and if a is if a is going to be large enough, then this will spread it out in this sort of domain. Okay, in this sort of domain M. So I need a to be large enough and have to have a lot of numbers after the decimal point. If I choose my a's correctly, this works. This works really well, and you can show it spread stuff out, and it's going to effectively be kind of random because it's spreading stuff out across the kind of the spectrum. It's giving you a large random number, and it's wrapping it around after it gets to M. Okay, and so this is something you can implement yourself, and it works pretty well if you're choosing your A's correctly. Okay, often you'd often implement this as in fact, you often internally, when you implement it, you do kind of x times a divided by 2 to the q. Okay, where q is kind of replacing the fractional part, where I'm again in having this large value q that I'm dividing by here. These sort of things, this tends to work pretty well. Okay, so this is just an example. If you need something concrete to think through, that will work pretty well to give you a hash function. So work reasonably well if I pick the a's and in this case the q in the right way.
Is that 2 times q or 2 to the power?
2 to the power q. Yeah, it's power's a little hard to write clearly. Maybe that's more clear. Okay, it's clear in the notes. That should be online. Okay, one thing I want to point out, don't do not do so modular hashing. Okay, do not do this, and this is h of x equals x mod m. Okay, where I'm the mod operation is I'm just I'm taking a large integer and I'm kind of wrapping it around. Once I get to m, I go back to 0. M plus 1 is 1, m plus 2 is 2, and so forth. 3m plus 4 is going to be the fourth slot. So then similar things are going to hash right next to each other. If I have two sets of objects that are exactly m apart, they're always going to hash together. Okay, and there's no salt or any randomness put in here. This is very commonly used, and if you use this, you'll run into some really weird kind of problems for hashing. Okay, it may work fine, but at some point it may give you some really weird results, and I've seen them. Okay, so I just want to say, do not do this form of hashing. This does not work. Things like these tend to work pretty well and will give you what you want. And for the purpose of what we're explaining, these will work fine. Okay, yeah. Well, you choose A. Oh, A and Q are chosen and fixed ahead of time. Those are kind of the seed or the salt, the salt, which is kind of describing how you make this deterministic, but that should be a random choice. Okay. Okay, and if for this purpose, you can use built-in hash functions in kind of random hash functions in Python or any place else. There are built-in tools for this. Just use that. Those should work fine for this homework, for instance, and for most of the stuff we do in class. If you're really optimizing some stuff, maybe some stuff we'll talk about later in the semester. I'll say where you have to be a little careful about this, but usually any of these things work pretty well.
So
Yeah.
do what we're hashing, why, what's the purpose? I think
Yeah. Okay, so what we want to do is model data that's coming from a uniform random distribution. We want to just look at some phenomena, and the distribution can model any sort of these objects. And I want to understand some properties of if I see a bunch of these things at random. And because these all have different non-uniform distributions, we're going to think about the simple uniform distribution. Okay, but this randomness is supposedly coming from data, but we're going to talk about instead the randomness is coming from the algorithm, and that's what a hash function gives you. And then here's how you implement this F part, which with the random string gives you something that spreads stuff out. Okay, and then we're going to just hash the numbers 1, 2, 3, 4 up to n to get n things. And if we use one of these hash functions, those n numbers we hash should be spread out over the domain of size m.
this
Right.
is to replace that.
Yeah, the observations will not be uniform, but we want to say, what if they were uniform? What should we expect to see? Okay, and it's some parts, if you haven't seen these things I'll talk about next before, they're maybe a little bit unintuitive. Okay, and I want to go over them because it's not what uniform data means is not maybe what you might, the first thing you would think uniform data, the implications of that. Okay, great, very good. Okay, so the first thing we're going to talk about is the birthday paradox. Okay, and who's heard of the birthday paradox before? You probably, if you've done, okay, so if a few of you, depending on what class you've taken or someplace, you've probably heard of this before. This is the phenomena that you have a room of, well, it turns out to be roughly 23 people. The probability that 2 of the people have the same birthday is about 50%. Okay, there are 365, 66 days of the year. Okay, so you think, okay, that would be unusual for 2 people to have the same birthday in a room of size 23. But about 50% of the time that's true. Okay, and we're going to see what this means in the context of this random distribution. Okay, so what we're going to think about is I want to kind of draw x1, these xi from x1, then x2 up to xn, okay, and when do I, and each of these, each xi is from this domain M, and we're assuming that the probability of xi equals j is equals to 1 over n, right? So this is our assumption. And when do I expect that 2 xi equals xj, this is I and j, for I not equal to j, right? So I'm going to have 2 things that have the same value, okay? So I'm going to have a collision here. I'm going to have my array, okay? Okay, and so let me draw a whole bunch of things here. Okay, so I'm going to draw the first thing. This will be x1. They're going to be random. This will be x2. This will be x3, x4, and then maybe x5 is in the same spot as x2. I've got a collision. So if I'm storing data in a hash table and all the data are different, the idea of the hash table is things should be spread out so that I can store stuff in a random place and look it up quickly without having to do a search, other than kind of index calling the hash function. But if I have a collision, then I can't use this anymore, right? So when should I expect to get this collision here? This is bad for a hash table. I mean, it happens, and the hash tables deal with it, but this is the situation they don't like to deal with. If they never had to deal with this, it'd be better. Okay, so when should I expect two things the same? And now this is the birthday paradox, right? This is the case where m equals 365, and I'm going to say that n equals roughly 23 people in the room, and I'm going to say, if I've run this, drawn 23 times with m equals 365, then it's probability about 50%, I'm going to have some collision where two people will have the same birthday. Okay, so if you're in the room, that does not mean someone else will necessarily have your birthday with 50% probability, but that two of the people will have the same birthday, right? Okay. All right, so before we analyze this, I'm going to run a simple simulation in class. Okay, so you should, I'm going to ask on you, and you're going to tell me a birthday, probably your birthday, but you don't have to share it. You can pick any birthday, but fix that in your head right now. March, April, May, June, July, August, September, October, November, December. Okay, so we're going to go through. I'm going to call people. You're going to say a birthday, and we'll see how long it takes until we have a collision. Okay, and we have way more than 23 people in this room, maybe 100. So we'll find one eventually, but we'll see how long it takes. All right, July 21, June 3rd,
May 23rd,
May 23rd,
March 20th,
March 20th, June 26th, February 14th,
23rd.
May 23rd. We've got a collision already. Okay, so this was, I've done this a number of times, and this was the fastest, I'm pretty sure. So this was 6. Okay, so we had a collision at n equals 6. Do you want to run it again to see if we'll do it? Okay, let's run this one more time. Blue now. We'll start the second one. March 31st,
August 17th,
17th, April 20, April 29, 19th,
January 21st,
Jan 21, July 25th,
July 1st,
July 1st, July 15th, March 19th, April 27th, November 22nd, May 24, November 20th, September 4th, July 11th, 5th, July 5th,
May 14th,
May 14th, May 22nd,
October 25th,
October 25th, January 20th,
December 8th,
December 8th,
August 31st,
August 31st, October 11th,
February 2nd,
February 2nd, October 2nd, June 20th, December 14th, February 18th, May 30th, okay, October 7th, December 12th, May 29th, February 12th, What?
May 7th.
May 7th? March 24? October 21st? September 21st? August 5th? December 9th? Oh, September 9th? What? June 17th? May 21? April 23rd? September 24th? October 12th?
July 11th.
July 11th? January 2nd? May 30th? Oh, there we go. Okay. All right. Very, very good. Very good. Okay, so did someone keep track of how many that was? This was. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. Okay, 46 times. All right. It turns out 46 times, it seemed like a while, but actually it's within the realm of what you should expect, as I will discuss in a bit. Yeah, so let's see, 40. Yeah, if you go up to 50 people in a room, it's about 3.5% of the time you will not have two people with the same birthday. So this was okay. So this was maybe about 5% of the time it would take this long. Okay, and this I don't have numbers offhand for 6 times, so we will maybe calculate that problem. Okay, so but it was not like 365, right? So it was much faster than that, where we got this either 6 times or either 6 or 46 times. Okay, so let's talk. I'll go through a bit of the analysis of why this is, just to kind of see why this is. So the probability of a collision, if n equals 1, is going to be so 0, right? There's only one birthday. You can't have 2 people with the same birthday. So the probability of collision with n equals 2 equals what? What's the probability of collision? Not 50%. If I only have 2 people, it's probably they have the same birthday. So it's going to be 1 over, the probability of collision is 1 over n. The first birthday is kind of fixed. And then the second person, what's the probability that they have that same birthday? 1 of m, because it's effectively random, right? Okay. What's the probability of collision with n equals 3? All right, let me do this approximately. You start to get a little bit more complicated form, but I want to first look at the probability that they do not, that I do not have a collision. Okay, so I have 1 minus 1 over m is the probability that the first 2 people do not have a collision. Okay, but now I can check the first and the second person, the first and the third person, or the second and the third person. I have these 3 things I can check. Okay, so each of them is roughly independent, right? We'll get back to this a little bit, but roughly the 3 things don't have a collision. It's the probability that 3 different things do not have a collision. Okay, So the probability they do have a collision is 1 minus that. So it's roughly equals this. 1 minus 1 over 1 over m, right? So that's 364 over 365, so a very large number, but to the power 3, right? And if you multiply things less than 1 to a power, they shrink. Okay, and so the probability goes up as the number of people I'm checking is going up. So the probability of a collision for a value n, without specifying n, if I generalize this, it's going to be 1 minus 1 over m to the number of pairs, and that's going to be n choose 2, right? So n choose 2 is the number of pairs, and this is going to be equals to n times n minus 1 divided by 2. So roughly, we're going to say n squared over 2. Okay, so I'm going to have roughly probably 1 minus 1 over m times n squared over 2. So this is roughly what the probability is going to be. Okay, someone with the calculating machine, plug in m equals 365 and n equals to 6 into this, and this will give a pretty good probability here of the probability of collision. Who wants to? This is for m 365 and n equals to 6. Well, my guess is still pretty small. My guess is about 10%, 8%.
Yeah.
Okay. So 0.048, right? So about 5%. So that's saying about, if you have 6 people in the room, took the first 6 people or any 6 people from this room, the probability, if their birthdays are random, would be roughly 5%, would there be a collision. So we got a pretty rare event on this side, and I guess about 5% on the back side as well. So yeah, okay. So kind of what happens if we put n equals to, so let me just quickly say, if you put n equals to 23 in here, okay, and okay, with the, if you put n equals to 23 in here, let's do for n equals 23, then this should come out to be about 0.977 to 253, which is going to be 1 minus this. This is going to be 0.532, right? So that's if you have n equals 23 people in the room, you get this goes over 50%. And so it gets up to about 50 people, it goes down to about 3.5%, or I guess 96.5%. Okay, so around 23 is when it crosses the 50% mark. Okay, so let me spend. I want to say, what I want to ask is, what is wrong with this like analysis? Okay, so what did we do wrong in this analysis? Yes, up the top. So bias. So it's not uniform. Yes, there are more birthdays in spring. I guess I read someplace that I think the modal date is going to be, but isn't like October or something like this, right? So it's not quite uniform, the birthdays on the different days of the year. If you look it up, it's pretty close, right? So maybe there are more B days in spring. But I think like the differences in the probability from one day to the next are like 0.0001 for different days of the year, right? So they're pretty close to unbiased, but they're not exactly uniform throughout the year. Okay, so this may change it a small amount, but this is not going to change it. It's not going to change it too much, right? If there were a subset of days that were much more popular, it might start to change it, but this does not add to too much change here, but it's not exactly right. You're correct. Yeah. Yeah, okay. The set of pairs, not IID, right? I said there are n people, there are going to be n choose two pairs. So I have to consider. Okay, so they're not exactly IID. This is a so yeah. Okay, so the way you phrase the issue is directly explained that way. Is a little bit more complicated, but the issue is that the way I'd like to illustrate this is this approximation works pretty well at the scale of n equals 6 or n equals 23, even n equals 46. This will give a pretty good approximation, probably up to 3 decimal points or so. What happens? What happens when n equals m plus 1? Okay, so let's say or m plus 2. Let's say I have 367 people in the room. Okay, and I went through this calculation. So 1 minus 1 over m to, let's say, m plus 1, choose 2, right? Even I don't use the kind of m squared over 2 analysis here, right? So what is this going to be? It's going to be, well, it's not going to be 1, and that's a problem. It's going to be something like 0.0000007, something like that. Okay, it's going to be some very, very small, or so 1 minus this, right? It's going to be 1 minus something very, 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 very small. So it's going to be slightly less than 1. It's not going to be 100% by this formula. This formula is not going to give me 100%, right? It's something very close to 1, but not exactly 1. Okay? And so that means it's wrong, right? Why does this have to be wrong? Because you're guaranteed a collision, right? The pigeonhole principle, apparently, if you have m plus 1 pigeons and only m holes, and they each go in a hole, there must be some hole that's shared, right? That means the birthdays have to collide. Okay, so by the pigeonhole principle, I must have a collision. But this analysis does not give me that. Okay, and the reason for that is that the probability of finding a collision as I go gets kind of gets larger and larger, because I know the first set of things I've seen already don't collide, so that I have some negative dependence to them. So I'm actually going to get analysis that looks like 1 minus n minus 1 over m minus 1 over m. This is for the times m minus 2 over m, right? So now this is the probability the second one does not have a collision. This is the probability the third one does not have a collision. It's not 2 independent things, but it's 2 things that have a slightly kind of lower probability. The third one does not have a collision is this one, and I multiply all of these things together. Okay, and eventually, if I have m, the m plus 1 thing here, this is going to be 0. And then, so I'm 1 minus something that's multiplied by something that's 0 is going to be equals to 1. Okay, so then if I get up to the n+1 thing here, this will have to be probably of 0 of not having a collision. And so then that means I must have a collision. So I didn't quite do the analysis correctly, but it's a pretty good kind of, it's an issue, small issue with the analysis. Okay, we'll do some simplifications in this class for some kind of to illustrate the main principles, but these are good things to check. Yeah, okay, but what else is wrong with the analysis? What else with birthday collisions did we not get right here? Let's go back to this bias question. Why else was this kind of process maybe biased? So leap years. Okay, so what happens in a leap year?
So there's been.
Yeah, so there's actually m equals 366, and that one day, February 29th, is less likely than all the other days. So this throws it off even more. Okay. Okay, good. Any other reasons that this might be biased? In particular with the class, like what would be a reason why in this class it would be kind of maybe biased? Okay, so not real. Okay, not the real birthday. If you had picked a random day, not February 29th, that wouldn't have spoiled something. But if you picked like a holiday, like if you picked December 25th, you're like, that would be a fun day to have a birthday on. Probably actually not a fun day to have a birthday on because presents only once a year. But if you picked one of those days not at random, then that could have spoiled the probability, right? Yep. Oh, so if someone's tired of this game we're playing, they're gonna pick a birthday that's up there. So yeah. So if people had not been honest, right? I asked you to pick a day and stick with that, but if you had not kept with it, yeah, you could have spoiled that. If you the way I did a random order of the class, I did an order of the class. If that was a random order, that's equivalent to kind of picking a random kind of subset of people without replacement in the class. So if the order was random, but maybe people with what was it? With May birthdays are more likely to sit in the front of the class, right? So maybe that would have spoiled it, right? There could have been relations with where people sat based on their birthdays, right? I know, like if if you look at people who play professional hockey, they usually have like a fall birthday because, or is it no? They have a summer birthday because they're usually the oldest kids in the class. They're the first, and in Canada, if you're older, you tend to play hockey, and then you're the biggest person, so you tend to stick with it because size really matters, especially at younger ages. So professional hockey players have a really weird distribution of birthdays because of some issues like this. For instance, yeah.
Well, isn't it also the case of like where we're in, but then we did it the second time, actually skipped the first row because we knew, so it's true random.
Yeah, it's not true random because I restarted. Yeah, so there are these subtle issues. I think that's probably going to be okay from a fresh draw. But if I had asked you all to change seats and then did it again, it would have been a bit better. Yeah, so these are things you need to worry about in doing this analysis. I think this was pretty good. I've had twins in the class before. They're both coming through the same age. They were twins. They both took the class at the same time, so they had the same birthday. Right? These are other things that can happen. And you need to be worried about, we're going to do analysis of things, but we're not going to, but sometimes it's not going to be a perfect modeling of the situation. And you have to assess Is the analysis wrong, or is my data and my experiments wrong? Was getting 6 or 46 outside the normal variation? They're both about 5% on either side, but I'd say that's pretty reasonable. I think I've gotten into the 50s before. So that was more, or maybe it was like 50, 51. So that was more unusual. But still, that could happen 3% of the time. I've done this about 10 times in class. So yeah, okay. So we're almost out of time, but I want to spend the last 5 minutes talking about one other little phenomena. And I may have to leave some of this to the notes for you to go over, but the coupon collectors is another common thing. And this is where you say, I have x1 up to xn IID from uniform on this distribution M. Okay, so the same setting as before, and I want to ask how many draws N until I see all J and M. So sum xi equals to J. Okay, so the answer here, oh, I forgot to say, the answer here for this question, how many, the answer, and I didn't spend time deriving that, I have n equals roughly square root of 2 times m. So it's roughly square root of m. So as m gets quite big, this, if m is 100,000, right? So that seems like a pretty big number. You only need like 100 people to get a collision. This grows much more slowly here. What do you think the answer is for the coupon collectors? How large does n need to be in order to collect all the coupons, right? McDonald's would have like a monopoly thing, and you wanted to collect all the properties. Like, how long until you collect them all, or all the toys in a thing of cereal? What do you think the number should be? Should be square root of n? No. 4m squared. 4m squared. I think that's about right, or something else? Closer to what? So about 5 times m? Yeah, it has to be larger than m, right? I have to see at least one of everything. But you think about 5 is enough? Anyone else? Any other guesses? All right, so who thinks it's closer to 4m squared? See hands. Who thinks it's closer to 5m? Who didn't raise their hand yet? Okay, and so for those who didn't raise your hand, give me another guess.
Great answer, but I know it's definitely between m and m squared.
Okay, good. So what's between an m and m squared? Give you a hint. As computer scientists, you should be more likely to guess this. Yeah, so the answer is about m log of m. In fact, it's going to be something like m times 0.577 plus the natural log of m, plus some lower order terms. Okay, so it's very close to m log m. So if you're a computer scientist, you see logs for binary search and for sorting. This is another place that log naturally comes up. You expect to see about a surplus of log m factor of things, so about m times log m things before you see one of each. Okay. The probability of seeing a new coupon, you analyze this, and I won't go through it. The probability of seeing a new coupon the first time, the first one is always new. The second one is probably new, right? It's most likely new. The third one is still probably new, but as you're trying to get that last coupon, it gets harder and harder to get. Okay. And so the last coupon, you expect to take roughly M draws before you get that last one once you have M minus one of them. Okay. And so you can write out that the expected, the number of N you need is going to be something like, it's going to be M times I equals 1 up to M of 1 over 1 over I. Okay, and so this term here is going to be HM, which is the harmonic number. And so okay, so this is kind of the probability of it gets closer and closer to 1 the earlier I is. So you have to do this in reverse order. This is the harmonic number, and this is known to, and the reason we know it so well is this is known to be about 5.77 plus the natural log of M. And so it's M times that. Okay, so the details are going to be in the notes, which are posted online. Start looking at the homework. You're going to simulate these phenomena on your own and try and compare against the analysis to see if your answers were about like you expected. Okay. Let me just turn off the streaming.
Don't worry.